Okay. Hi, everyone. Welcome to week 2 of the ACE Premium Workshop on Learning Without Labels. I am Dr. Shazia Akbar, and I will be teaching you about the unsupervised learning of deep clustering models today. I am a machine learning engineer at Altus Labs, and previously was a postdoc at U of T and an affiliate of the Vector Institute. And I worked a lot on unsupervised learning whilst I was doing those two things, and hopefully I will share with you some of the techniques that I came across during my training. So before we jump into today's sessions, I just want to give a quick recap of what we talked about last time. So we briefly went over the different types of learning we can adopt when we're using deep neural networks, as well as other machine learning techniques. And we dived a little bit into unsupervised learning, particularly autoencoders, which are almost like a mapping function between inputs and outputs, and variational autoencoders, which enforce a regularization term within the loss function by introducing unit Gaussians within the latent space. We talked about disentanglement and how we can change VaDE to force it to learn more disentangled features. And then finally, we touched on GANs a little bit as well. So following on from that, I kind of want to go into a little bit more techniques which are technical and adapt the loss function a little bit more to incorporate more knowledge. So today we'll really be focusing on clustering techniques. I'll start off with a quick brief overview of commonly clustering techniques that you've probably used or at least came across before. And then we'll go straight into one particular deep clustering technique called VaDE, as well as touch on other clustering techniques. And lastly, I'll talk about predictive modeling, which is an upcoming, really interesting field in unsupervised learning. And I think it has potential moving forward as well. So let's start off with the very general term clustering. So when we talk about clustering, we're talking about grouping together a set of objects, or in the case of training and deep learning, a set of data instances which are similar, and grouping them together, and also separating them from other objects which are very dissimilar. So usually there's some sort of distance metric in play as well, such that clusters which are more similar are positioned closer together in a high dimensional space, and those that are dissimilar are much further apart. So really, when we're talking about clustering algorithms in general, we have two terms, or two components rather, which are key ingredients to creating the perfect clustering algorithm. So one is a proximity measure. So we need to know that when we say very similar and not very similar, what we mean by those two terms, and computing them and giving an actual value as to what we mean by similarity. And also, we need some sort of criterion function to evaluate a cluster. So we need to know when we have a good cluster and when we have a very bad cluster. So here I've drawn two kind of very coarse examples here using a few data points. And so we want clusters that are that group together multiple objects. So we don't want ones that are separated apart, like we can see here. But we also want it so that it gathers sufficient information from the data, and not too much and not too little. So we need some sort of function there to really determine what we mean by good and bad clustering. So I think to start off with, we'll talk about K-means clustering, which should be familiar with most of you. It's a very simple clustering technique, and it assumes some sort of Euclidean space. So when we talk about the distance in a K-means clustering algorithm, it's usually the Euclidean distance between data and clusters. And what happens in K-means clustering is that we measure the distance between, first of all, we randomly assign clusters within a high dimensional space, and then we measure the distance between cluster centers and their instances, that all the instances within our training set. and assign the cluster labels depending on which cluster has the minimum distance from each data point. And then we update all those cluster centers based on the mean of all those data instances which were associated with that particular cluster. And then that cluster center should move somewhere else to a different space. And then we can repeat this process until that cluster center doesn't move as much anymore, when it's settled into a state whereby the data instances around that cluster are keeping that cluster where it should lie. So it's a very simple technique, but it's used across many subfields in machine learning and deep learning because of its simplicity. And because it doesn't make really any assumptions about the data. The only assumption really here is the Euclidean space. Another well-used clustering algorithm is expectation maximization. And the problem with K-means is that it's a very greedy approach, and the initialization is kind of very dependent on what kind of randomization functions you had, what kind of seed you fed into your random variable function. Whereas here, we're really trying to model the data rather than just kind of randomly start off with a random initialization and shift and move this cluster center to where it should sit. So there's two steps. There's an E step and an M step to the EM algorithm. The first step is to first use the current model to estimate some sort of labels for unobserved data. So I should mention we have observed and unobserved data, and by having a complement of both, we're essentially testing how well this model is working on the unobserved data, and then updating our model on what we know about our data. So the first step is to estimate the labels and calculate an expectation likelihood function. And then the M step is actually updating the models, and we'll repeat that until convergence. So really here, we're using Gaussian representations to model what our data looks like. So both EM and K-means are fairly familiar. And they have here's a visual representation of expectation maximization as it creates two Gaussian representations here. So these two functions are fairly simple. And we would expect that some of these techniques can be transferable to deep neural networks, but we'll actually see that because of the way deep neural networks are optimized, we need to have a slightly different approach to how we create these two clusters in this case. So when we move to deep clustering techniques, we kind of have three ingredients within our model itself. So we have a deep neural network, which will learn the complexity of the data and what the data looks like and the abstract features within our data and so on and so forth. We'll have a network loss, which it determines how well the data is represented within the deep neural network. And then we have this clustering loss as well, and that can take many forms, and some of them are shown here. But this is kind of an additional restraint on the optimization process in order to create defined clusters which capture key components within our data, and kind of measure that similarity, dissimilarity that we mentioned before as well, but in a slightly different manner. So the other thing I want to mention before we get into the details of deep clustering is performance metrics, because when we're clustering, we don't really have a way of measuring how well we're doing. And there are other ways we can measure. Sorry, my voice has just gone there. So we do need some way of measuring performance within our clustering algorithms, and there are some widely used metrics that are used in this field. One is unsupervised clustering accuracy, which can be shown here, and it kind of takes properties from a traditional classification accuracy, but has a mapping function here. So we have a mapping of that cluster and then comparing it to the labels. We also have normalized mutual information, which is a measure of correlation between two clusters. So here our two clusters are Y and C. And there's luckily for us in sklearn, there are actually built-in functions to measure all of these properties as well. Similarly, for adjusted rand index, there's another sklearn metric function to measure this. And ARI is considering all pairs of samples, so it's slightly better than the normalized mutual information in that we're kind of looking at pairs of samples rather than two at a time. So I would actually like everyone to have a look at these in the practical session when they've kind of defined their clusters and want to know how well they're performing, because these are great metrics to use, and I think not everyone uses them within the deep clustering field. So let's get on to the deep clustering algorithm part. Before I get started, I would like to point you to this particular paper, and it was a really good resource for me as well when I was looking through the field in general. It's kind of like an overview of all of the deep clustering algorithms that are out there, and also gives like a really nice illustrations of these different clustering techniques as well, and groups them together into nice little sections. So if you just want to have a glimpse, I'd highly recommend this paper here. So today I'm going to be talking about VaDE, which is a variational deep embedding algorithm. And this is a paper, and it's available on arXiv, so you can download it and have a look at it. And it's being used quite substantially in the field as well, and has been around since 2017, so a couple of years now. But it fits in very nicely with a topic that we were covering last week, which is why I kind of selected this as a practical, because we can reuse a lot of components that we created last week. So just as a quick recap, we talked about variational autoencoders as a network architecture that builds on top of an autoencoder by having a latent representation composed of unit Gaussians. So here are our unit Gaussians here, which have a mean and variance term. And instead of decoding directly from a latent code representation, some sampling occurs first, and then the decoder component then reconstructs the original input. So the loss function here is optimized to reconstruct the original input data, but also learn a latent representation which models the data distribution accurately as well. So VaDE actually works on top of a variational autoencoder in that we have both an encoding term and a decoder term as well. And the task that VaDE needs to perform is to generate new samples, which we were doing already. So this is the generating new samples component shown on the left here. But in addition to that, the VaDE algorithm also performs clustering by learning these deep embeddings right at the top here. So this is our encoder component. And again, feel free to look at the paper for further details. Hopefully we'll cover all the details you need in order to implement this particular algorithm in the practical session. So when we look at VaDE in greater details, we have our clustering encodings here, our clusters, learned here. And these clusters are parameterized by this pi term here. And when we're selecting clusters or defining clusters, we're actually using a Gaussian mixture model. And for those of you who are not familiar with Gaussian mixture models, our friend, the unit Gaussians, comes back into this architecture, into this, learning algorithm. And the purpose of the Gaussian mixture model is to learn a series of unit Gaussians which fit to our model accurately enough so that when we sample from it, we get something that could have originally came from our original training set. And if we've modeled this Gaussian mixture model for long enough and in a sufficient manner, we should be able to achieve that. So we should be able to achieve a function that can capture all of our training set. And this is dependent on the number of Gaussians we define as well, and that's a parameter that you can set. I also should mention that we may use EM to update this model because EMs also work on unit Gaussians as well. So EM often used to do this optimization process as well to update the model. So in PyTorch, actually learning that PyTerm is very, very simple. All we have to do is take our encoder, decoder component, which has already been trained to a level, and take some of the encodings from that neural network and push it through our Gaussian mixture model. And here we've defined the number of unit Gaussians, and you can define other parameters as well. But then all of your terms that you need kind of come from that single Gaussian mixture model. And these are all shown here. So you can reuse this in your code as well in order to get these variables. So how does VaDE work if we go through it a little bit more detail? So I'm going to go through this back to front. And the reason I do this is because this is the way the authors kind of showcase this algorithm. It just makes a lot more sense to talk about the decoder first and then the encoder. So first, what happens is that a cluster is picked from our Gaussian mixture model, which you saw earlier. And then our Z encoding is suddenly not just dependent on the mean and variance from our unit Gaussian representations, but also the selected cluster as well. So it's kind of got 3 inputs here in order to compute this Z. And then the Z is similarly decoded to an reconstructed X, as you would do in a traditional variational autoencoder. So this is our decoder term shown here. And then our encoder representation encodes another X into a latent representation. And by doing that, it goes through an optimization step, which we will talk about in a minute. So it goes through the loss function, and then all of these weights are updated as a result. So I already mentioned pi here, which is what we sampled from in order to, is how we selected that one cluster that we talked about earlier. The mean and variance of the Gaussian distributions are shown here. They can also come from the Gaussian mixture model, which we saw earlier with the PyTorch code. And the K terms here are the number of clusters that we want to define within our VaDE architecture. The VaDE loss function is, again, an elbow term, and it's composed of a joint probability of the input X, the encoding from the latent representation, as well as the selected cluster. And as well as that, we also have probability of Z and the cluster given X, which is our decoder component. And it's something that we've seen already within the variational autoencoder, so it's fairly easy to compute as well. So this term here, which I just described, has been expanded out by the authors, and the details are given within the paper itself. But a lot of terms here, like the probability of X given Z, the probability or the log likelihood of Z given X, are things that you would normally have within a variational autoencoder. The additions are the encodings given the cluster that has been selected from the Gaussian mixture model and the probability of that cluster as well. So all of these together make up the elbow term, and it's all conditioned on the cluster that has been selected. So the authors take this one step further and expand this out to really the raw mathematics behind the mathematical function. And it may look a little bit scary to begin with, but actually we can break it down into smaller components, including a cross-entropy term where this looks exactly like the binary cross-entropy term that we looked at last week, where we have our means of our Gaussians here, as well as our input X. We also have some sort of comparison of the cluster C to all of the other clusters within that Gaussian mixture model representation as well. So that unit Gaussian representation, where here we have the variance, and again, the mean of the cluster that was selected, as well as the means of all the other clusters as well. And we're also including some sort of probability of C, which is a prior that came from the Gaussian mixture model. So a combination of all of these different components weights the ability to find similar embeddings and components within our VaDE deep embedding, as well as the reconstruction that happens normally within a variational autoencoder. Now, the implementation.
Sorry.
Go ahead.
Excuse me, I have a question here.
Yeah.
So I just want to check with the clusters that you say that, and I think it's clearer in a couple of slides back. It sounds like that there's a correspondence with the Gaussians that are in the normal variational autoencoder in the latent space, that there's a direct correspondence between those and the Gaussians for each individual cluster. So is there like a one correspondence between them?
So here, the unit Gaussians are essentially because the length is the same number of clusters we have, each cluster should theoretically be represented by a unit Gaussian within this entire framework. So yes, there is a strong correlation between the clusters and the unit Gaussians we have.
Okay, thanks.
Thanks. So there is a fair bit of mathematics behind this, and the paper goes into it in a little bit more detail, but I actually found it very useful to look at the original implementation, which also is available on GitHub. The code is in TensorFlow, and there are PyTorch versions out there as well, but my suggestion would be to take the TensorFlow code and just translate it to PyTorch, because it's a really nice way to understand what's happening and also create your own code at the same time. So if you're feeling very adventurous, feel free to start in PyTorch and try and implement it from scratch. But I find this a good reference as well.